Okay, so we're going to do one more screen capture video here because I'm going to really lean on the 3D structure of molecules for this part as well. So we're going to talk about polar molecules, polarity of molecules. So you've got two situations. You've got polar molecules and non-polar molecules. And so polar molecules have areas in the molecule of uneven electron distribution. They have a positive area of the molecule and a negative area of the molecule. And this is going to lean very heavily on the idea of polar bonds from the last chapter, but there is a difference. So a bond can be polar, but that doesn't guarantee that the molecule is. So you have to have polar bonds to have a polar molecule, but you can have non-polar molecules that are made entirely out of polar bonds. We're going to talk about that in a little bit. But essentially what it is that these bonds have dipoles associated with them. We talked about this in the last chapter. The bond has an area of positive and negative charges, but these can cancel out on an overall total molecule. It has to be an uneven charge across the molecule, and we're going to talk about this. And so one way to think about it is to consider this little flow chart I've made. And so is a molecule polar or nonpolar? Well, does it have polar bonds? If your answer is no, it's got to be a nonpolar molecule. Everything is being equally shared. Yes, well, then life's going to get a little bit more complicated. We've got options still. And so you have to go, okay, well, do they cancel each other out to the dipoles of these polar bonds? Do they sum to zero? And we're going to show that with some 3D representations in a little bit. But if the answer to this question is yes, well, you have polar bonds, but you have a non-polar molecule. Now, if the answer is no, if they're not canceling out, that means the molecule has an uneven distribution of charge across it somewhere. An uneven net distribution of charge, I should say. And that gives you a polar molecule. All right. And so again, we're going to lean on our Lewis structures from earlier. So let's look at like CO2. So carbon and oxygen. This is a polar bond. Oxygen is more electronegative than carbon. Electrons are going to be pulled towards the oxygen. But here's the issue. Guess what's directly across from it? Another oxygen. They are going to pull electrons to the left and the right, and they're going to cancel each other out. And so when we look at, whoops, still got that guy in there. When we look at CO2, it's a linear molecule. And so there's going to be a dipole associated with this bond, a dipole associated with this bond. You have an arrow pointing towards this oxygen, an arrow pointing towards that oxygen. They both are going to have the same strength because it's carbon and oxygen, both double bonds. They're going to cancel out. They're going to add to zero. They are going to be mutually destructive. And so you have a nonpolar molecule. So CO2 is composed entirely of polar bonds, but it is a nonpolar molecule. Now, if we look at something like, oh, that can go away too. If we look at something like water, H2O here, clear this out. Go oxygen, hydrogen, hydrogen, get 3D of that. This has polar bonds. Oxygen and hydrogen are going to be polar, so that's a polar bond right here. This is a polar bond right here. And they're not going to cancel out because this oxygen is not directly across, or I'm sorry, this hydrogen is not directly across from this hydrogen. And so what you have is you have an area of partial positive charge over here, partial positive charge over here, negative charge over here. And so you get an area down here that's partially positive. You get an area up here that's partially negative. So you have what we call a net dipole across the entire molecule. And so just like we could label dipoles on a bond, now we can label molecular dipoles. And I know it's something Avogadro can do. I don't think this program can do it. Oh, there it is. There's our net dipole. So as you can see, there is a dipole here. Now if we went to something like, oops, NH3, take a second, think, would you expect this to be, something that would be polar or nonpolar? What do you think? Well, the answer is that it has polar bonds, so we're on the right track. And they're not going to cancel out because they're not all directly across from each other. These are not flat with 120 degree bond angles. These are 109, well, actually a little under 109.5. And so you're going to get, because of the asymmetry of the molecule, you're going to get a net dipole moment. And again, we can actually cancel that or calculate that. So here it is for the bonds. And here's the overall. So again, it's going to be negative over here, positive down here. That's what we're looking at. So each of these bonds, you have a negative region, positive region. You can play around with it if you want. And essentially that's all we're talking about. And so the last thing is, we'll look at like carbon tetrachloride here. So, actually we'll look at two more. So we'll look at carbon tetrachloride. So Cl4, 3D model that. All these bonds are polar. That's a polar bond, that's a polar bond, that's a polar bond. But they all cancel out. And so if we calculate a net dipole, playing a dangerous game here, we don't get one because of the symmetry of the molecule. Even though there's not ones that are directly opposed, in some, they all cancel each other out. And so, this one has a dipole of this, of this direction. It would be pointing towards the more electronegative chlorine. But same here, and here, and here. And so this used to be a very common nonpolar solvent, and it turned out it was incredibly carcinogenic. So chemists had to move away from it. But it was great. It didn't catch on fire, all kinds of good stuff like that. But that's a nonpolar molecule. Now the other example, the last one we'll do, is CH4, methane. Look at the 3D structure here. And again, we get the same sort of idea. They would all cancel each other out, but also these are typically considered nonpolar bonds. So carbon and hydrogen is typically a nonpolar bond. Your book gets a little squirrely about that, but out in the world, people tend to consider this a nonpolar bond. And so this would be something that would be made out of all nonpolar bonds. So this would also be a nonpolar compound. So it would actually end up going this way on the flowchart, and you'd end on nonpolar molecule over here. So if you've got polar bonds, you have to ask the question, do they cancel out? And then you have to consider the geometry. So it gets a little bit tricky. And so the idea of geometry factors in very strongly to this, and it really loops back in with the idea of polar bonds from the last chapter. So you've got to really stitch those two together to understand this. But once you get the hang of it, it's not too bad. So I'll have a practice worksheet you can work on. And again, it'll be just starting out from like, if I just give you a formula, if I'm like, oh, hey, NH3, is that polar, non-polar? I expect you to be able to answer that type of question. So you want to get to that level. All right. And enjoy the worksheet.